All right, let's continue with what we had before. So far in chapter 7, we were trying to study something which can be written in the matrix form. So we're solving something called linear ODE system with constant coefficient. And we know that actually we need to differentiate the cases according to what kind of eigenvalue and eigenvectors we got from the matrix A. So two distinct real that's one case. And we are going to have two straight line solutions. We are going to determine if it's a source, saddle, or a sink. So that's the first one. The second one is we can have one repeated real. That gives us something like this. Okay, or something, goes out. Again, it depends on if lambda is bigger than 0 or less than 0. And then we have two complex. We are having three cases, spiral n, spiral source, spiral, and finally a center. Of course, we can also have what we call degenerate cases, where we have 0 eigenvalues and such. So now what we want to do is we want to summarize everything into a quick table. Okay, so this is what we want to do. We want a quick access to the phase portrait. We know this depends on lambda, and we know the lambda depends on matrix. Therefore, if we give you a random matrix with 4 numbers, can you just quickly see the 4 numbers and do some simple calculation and then determine, which kind of situation are you going to have? That's what we want to do next. Of course, you can always go ahead and solve the whole process, but what we want now is some quick access. In the same spirit as, can you draw the graph of this? The answer is yes, I can draw the graph of this. It's going to be a quadratic. But if I just quickly look at this 3, I can get some information, not all the information though, that this one has to be this instead of this. Okay, so now we're trying to do the same thing for what we have done so far. If we just care about which type of equilibriums do we have, which kind of phase portrait do we have, can we just do some quick calculation in order to get this, instead of doing the whole process to find all the lambda, all the vectors, and finally do the assessment? That's what we want. Okay. To do that, we need to investigate what's going on with the process and then start to cut off the parts which are not important. That brings us to the idea of the trace determinant plane. The idea is quite easy. Okay, so what you have is this. You have a matrix 2 by 2. You want to compute the lambda. So that's certainly something you can do for general numbers, not just for some fixed number. Then what you have is D minus BC. And you can do it in this kind of way. We know which kind of solutions, phase portrait we have really depends on which kind of lambda we have, which kind of solution we have for this quadratic. Therefore, what's important is just this number and this number, because they are going to determine what the final lambda is going to be. So I'm going to call the first one T. I'm going to call the second one D. And now let's see what is T. T equals A plus D. What is it? That is what you have in the matrix. And that's the sum of all the diagonal elements. We give this one a name. It's called the trace of A. Okay. Second, we have D. D equals AD minus BC. What is it? It's very easy to see. It's actually the determinant of A. Okay. So what kind of lambda do you have? It really depends on two numbers. The first number is A plus D. The second number is AD minus BC. Moreover, if we take a closer look, we figured out actually it depends on the first number, which is the trace, and the second number is determinant. So lambda is determined by T and D. Okay, that's the original idea. That if I have a quick matrix, I just quickly calculate these two numbers, and just by looking at these two numbers, I will know which case I have out of all these possible cases. We will call it a TD plane. Okay, so that's what we're trying to do. Great. Number 3, something I want to mention. T and D are invariant under change of basis. Because for the same system, as we mentioned before, whenever you change the basis of the original problem, you are going to have different kind of matrix. However, the dynamic does not change. It just shows differently in terms of the matrix. Now, what you can verify by yourself is it doesn't matter which kind of basis you take. Your matrix may look different, but your trace and your determinant will always look the same. Therefore, this kind of information does not vary according to a change of basis, which is great. It's the same thing as a distance is fixed no matter which coordinate system you take them. Even though the point under two different coordinate systems may be different, but the distance stays the same. So it's invariant, which means it's reliable. Otherwise, if you change the base and you find a different matrix for the same dynamic, you may have different trace, which give you a different behavior, which does not make sense in real life. Okay? As long as the phenomena doesn't change, you should receive the same result, no matter which coordinate system you pick. You can verify this by yourself. I will give you some some hint. The first one is you do have a very simple fact you can prove. That is the trace of A times B equals trace of B times A. With that, you can try to verify the trace of A equals the trace of D, which is actually the sum of all the lambda, where A equals PD P inverse, which is a change of coordinate operation. Second, to prove determinant, you can also prove it because determinant A times B equals determinant A times determinant of B. Therefore, determinant of A equals determinant of PDP inverse is going to equals determinant of D. Because determinant of dp and the determinant of p inverse cancel each other. Okay, that is based on the property of determinants. If you think about it, it kind of makes sense because determinant describes how your area is going to change after you do a linear transformation. Okay, so of course if you change it and you make the area twice as large, and then you change it again, make it triple as large, then together it's 6 times as before. Okay, but that's for your exercise to try to prove these are invariant, which makes them really nice property, because no matter which coordinate system you pick to describe your system, you will always receive the same trace and the same determinant, even though for different matrix, and therefore you are going to receive the same behavior of your solution. Now, with that, we are ready to establish the trace determinant plane. We already know that the characteristic equation really just depends on two numbers, t and d. Okay, and we can further solve it. We can have it's t over 2 Then we can see, well, do you have two complex? Do you have two distinct real? Do you have one repeated real? It really depends on what's the value of this. Okay, if t squared minus 4d equals 0, then you have t plus minus 0, you only have one repeated real. If t squared minus 4d is bigger than 0, you have two distinct real. Because you can take the square root of a positive number, you can always get something real. And then when t squared minus 4d is less than 0, you have two complex. Okay, so now if we draw the TD plane, and we put this thing here to be t and a d, then this one give you nothing but d equals t squared over 4, which is a parabola. So it's going to be a little bit flatter than this. And right on this parabola, okay, on this parabola, you are going to have repeated real value. Similarly, you can actually try to do it by yourself. If it's t squared minus 4d is bigger than 0, that means d is less than t squared over 4, which means it's below the parabola. You will have two distinct real, and if it's above the parabola, let me see. Let's make it a little bit smaller. Okay, and if it's above the parabola, it's gonna be two complex. Okay, just by looking at the determinants of the quadratic, we can have these three cases. Okay. So now it's settled. We have a lot of graphs. We have the repeated, real, one is a sink, one is a source. Okay, and these two should go on onto the parabola. Okay, we have two distinct real, so we have three possible cases. And then one up, one down. It really depends on which direction you have. Okay, that's for two distinct real, and that should go below the parabola. And then finally, we have the complex pairs. Source, and then center. Center. We can even have zero eigenvalues. That's when we have let's see. Yeah, that's not important. Let's put it at the last. Okay. So now what we want to do is we just want to put all these corresponding properties onto this graph. So next time, if you see the location of your TD points on the TD plane, you will be able to tell right away, okay, which kind of situation do you have. So let's give them a different color. Okay, let's give them some picture to make them look nice, like a picture. And then our job is try to put all the corresponding pictures into the right location on this TD plane, so we can know which case we have in general after we compute TD. Okay, I probably want to make them smaller in order to later put them together. Do I know how to make them smaller? Yes, beautiful. Okay. Our job is try to put them all there. Okay, let's do them one by one. The first case we have is number 1. D equals t squared over 4. Okay, That's one repeated real lambda. And because it's on the parabola, this is 0. Therefore, you just have t over 2. This one repeated itself for twice. Now it's very easy to see. Which case do you have? Well, for this one, I require lambda to be bigger than 0. But then, it's the same as requiring t to be bigger than 0. Okay. For this one, I require lambda to be smaller than 0. Then it's the same as to require t to be less than 0. Okay, so it's settled. These two goes on the parabola, and this one requires t to be less than 0, so it should be on the left. This one requires t to be bigger than 0, so this one should be on the right, on the parabola. So which one do you have really depends on, are you on the left-hand side or right-hand side plane, left half plane and the right half plane of the original TD plane. So these two are settled. Next, let's do the complex. That requires t squared minus 4d is less than 0, which is above. So that is the same saying like d is bigger than t squared over 4. Okay, above the parabola. So it goes roughly here. Okay, so which case do we have? Let's go back and look at lambda again. We already know this part gives us the imaginary part, so it's the I, because it's less than. Okay. Then from here you can see the real part really is just t over 2. And the other part is the leftover, but it only tells you the imaginary part. Good. Now which case do we have? We just really look at our lambda. For this, we need lambda less than 0. Not lambda, real lambda. Okay, which means hold on, this is a source, so bigger than 0. Then you just require t to be bigger than 0 because t over 2 is your real lambda. This one requires real lambda less than 0. This requires t less than 0. And finally, to have this, you need to require t equals 0. Okay, so it's settled. Make sure when you put everything, number one, they're above. Above the parabola. Okay. Second, for t equals 0, you have exactly the center case here. Okay. For t bigger than 0, you have exactly the source case here. Okay. Above and to the right half. And finally, t less than 0, it's here. Did I do it again? Oh, I see where the problem is. I took both of them to be a sink. This one should be a... Although I took both of them to be source. This one should be a sink. I keep doing that. Okay. Sink on the left, source on the right, depending on which t do you have. So these two are in the right position. Now you can see our only job is try to put these three into the right place below what we have here. Okay, so number 3, finally, two distinct real. Which is actually below. Which tells you t squared minus 4d is bigger than 0. So that's how we got it. All right. So what do you have? You still have lambda equals t over 2 plus minus t squared minus 4d. And 2 really doesn't change a thing, right? We just care about lambda is positive or negative. So we really only want to focus on the top. Okay. So what do you have? It's gonna be a little bit messy. So how about we actually differentiate them into two different cases? Okay, the first case is number 1, t bigger than 0. Okay, later we're gonna do the second case where t is less than 0. Okay, if t is bigger than 0, which means what happens on the right half of the trace determinant plane, to get this, we want lambda less than 0. We want a t plus and a t minus to be bigger than 0. We want these two to happen. Okay, this will always happen. Okay, no problem. This will not be guaranteed to be bigger than 0 unless t is bigger than what's going on here. From here you can see this is t squared if you square it. This if you square it, it's going to be t squared minus 4d. So in order for this to happen, you just need to require d is bigger than 0. As long as d is positive, t squared minus 4d is going to be less than t squared. This will work. Okay, so that's mistake. That's exactly the source case. Okay, that's where we have. Now let's go to the next one, the sink. Okay, we want lambda to be less than 0. Okay. In order for lambda to be less than 0, you want this to be less than 0. And you can see there's no way this can happen because this one is always positive, so this never happened. So this cannot happen if t is positive. All right. Now, what about one positive, one negative? This again is going to be positive no matter what. So in order to have one positive, one negative, all you need to do is just require this one to be less than 0. That requires d to be less than 0. Therefore, t squared minus 4d is going to be bigger than t squared. Therefore, if you take the square root, the negative 1 is bigger than the positive 1. Together, they become negative. Okay, so the key here is try to look at your d when t is bigger than 0. Okay, if d is positive, you get the source, and if d is less than 0, you get the saddle. There's no way you can get a sink. Okay, so far, so good. And then, of course, we wonder what's going to happen if d equals 0, because I do have the d bigger than 0 and d less than 0 case. Well, let's see. All we need is, okay, if d equals 0, we have t plus positive. All right. If t is less than 0, we do have t minus. So d equals 0 actually gives you the 0 eigenvalue case, which will give you something like this. On one direction and on the other direction. Now, on the other direction, it just doesn't move. So what you have is a lot of parallel. And each one is going to be a source. This is not so interesting, and it's very easy to do in real life, so we don't include this case in the plane. But I mean, just want to let you know that we do have this case. We just think it's not important enough, and it's rare enough that we don't see them in real life. Okay, so skip. Doesn't mean that we cannot do it. It's just it's very rare and not interesting. All right. So that means what? Let's see how to put everything in. So what we have is, let me see. It's gonna be a saddle if d is less than 0. Yeah, let's finish everything. Let's finish everything and then come back to do this. The other half is really quick. Okay. B, t is less than 0. We'll repeat the same analysis. Okay, we have lambda equals t plus and t minus. All right. Okay. Now, to get a sink, we need both of them to be negative, right? From here, you can see this one is always negative, no matter what. Because this is negative, you minus a positive thing, okay? It's always going to be negative. The key is try to keep this one negative. How do you keep this one negative? Now again, t is going to be a negative number. This is going to be a positive number. It really depends on which one is bigger, okay? So to make the whole thing negative, you need to make sure the negative one is bigger in terms of absolute value. Therefore, your d has to be positive. All right, similarly, you can think about this is going to be a saddle, and d is less than 0. We'll make sure that happens, because when d is less than 0, this number is bigger than this number. Therefore, this one is going to be positive. Okay, and this one is always negative. So you have one positive, one negative. It's going to be like this. Okay, d equals 0. Again, we have the 0 eigenvalue case. But this time, it's going to be one negative eigenvalue. Okay, and one 0 eigenvalue, so you have some case which looks like this. That's basically what we have. Okay, so now let's try to put them on the graph. What we can do is, let's summarize them. Okay, so note, this gives you a saddle. Okay, in the first case, this also gives you a saddle, which means regardless of your t, if your t is bigger than 0, but d is less than 0, you have a saddle. If t is less than 0, as long as d is less than 0, you also have saddle. So everything below d equals 0 is going to be a saddle. Doesn't matter which t you have. Doesn't matter which t you have, you will always have a saddle, as long as your d is less than 0. No matter what. All right. Now when d is bigger than 0, and the t is bigger than 0, that will give you a source. Which means t is bigger than 0. Oh, okay. T is bigger than 0. And the d is bigger than 0. So here. Below, but above d equals 0, you will have the source. Similarly, you will have your sink here. All right. That's roughly all the possible cases we can have. Okay, now what I want to do is I want to switch. Actually, let's not switch. Let's just copy this one and try to use it to do a quick example. Okay, copy, paste. So that's the whole analysis part to get this table or diagram. But once you have the diagram, you can just use it without having to worry about where it comes from, because basically it's just a summary of what we have done in chapter 3. Okay, so this is our final product. This, okay, trace determinant plane. That's this one big picture we just did, okay, with all our knowledge. All right, now let's take a look on how to use it. Let's say we got a system. We know A is going to be 2, 2, 1, 3. Now before, in order to know which kind of behavior you have to complete the whole process to calculate lambda and everything. But this time you don't have to. You just look at T, which is 2 plus 3 equals 5. Okay. You look at D, which is 2 times 3 minus 1 times 2, which is 4. Okay. And you look at T squared. T squared over 4, which is 25 over 4. It's bigger than D equals 4. Okay. So you know it's above the whole thing, above this parabola, plus T is positive, therefore it should be this one. It's going to be a spiral source. Okay, again, it's above the parabola. Okay, and T is positive, therefore you have this case. Done. All right, try another example. A equals 2, negative 2, 1, 3. Trace 0. Determinant negative 7. So what do you have? You have the trace equals 0. Okay, T equals 0, which means you are already on this line here, the vertical line, y-axis, d-axis here. Okay. Meanwhile, your D is negative, therefore it's this case. Automatically, you know it's going to be a saddle. Case. All right, so that's all we have. Okay, on how are we supposed to use this TT plane? Basically, we just completed everything we have done before and put them into a shortcut. This time, every time you have something, you can just use a shortcut to assess which kind of case you have. Okay, it's pretty neat as long as you memorize what's going on here. Of course, you don't have to, and if you choose not to memorize this or not to use it as your hand at your hand, then you probably have to go over the whole process. But with that, it's so quick to check what's going on. All right, that will be all for today.